So today we're going to continue looking at motion with constant acceleration. So previously we derived these two equations below concerning motion with constant acceleration. Both these equations involve time. So a question can be asked, is there an equation that can describe the motion if we do not know the time? And the answer is yes. So we can derive an equation that is independent of time by first analyzing the velocity versus time graph for constant acceleration. So below we're going to draw a velocity versus time graph with a initial velocity and a random velocity at point x. So the first thing we can note is that just as for an acceleration versus time graph, the velocity at point x minus the initial velocity is the area under the curve. For the velocity versus time graph, the position minus the initial position is equal to the area under the curve. So just analyzing this graph, we can draw out the first rectangle here, which is associated with the initial velocity. And then we can also note that this distance here is the final velocity. And we can also note that the slope is equal to the constant acceleration. And then we can also note that this distance here is the velocity at position x minus the initial velocity. And we can note that that quantity is also equal to the acceleration times time. We saw that in our last video. So now since we know that x minus xo is the area under the curve, we can use the diagram that we just drew to find a second equation for area under the curve. And this will help us to find an equation without a time dependence. So if we draw the same graph and label these two areas here, split it up into area 1 and area 2, we can also label our side length values, which we saw above. So to find the total area, we're going to need to add the area 1 plus area 2. And so for area 1, we got this rectangular box here with a width of t and a length of VOX. So the area is just going to be VOX times t. And then for area 2, we have this triangular area here. And I just want to know how to find the area of a triangle. It's going to be equal to 1/2 base times height. So I draw a little diagram here of a triangle with the label for base and height. So for us, it's going to end up being 1/2 AX t squared. So now we have everything we need to solve for the total area. Just remember that we're solving for the area under the curve. So I'm going to start using that instead. And so if we add area 1 and area 2, it's going to be equal to VOXT plus 1/2 AXT squared. So now that we have two expressions for the area under the curve, we can equate both of them. So the first expression and the second expression are right there. So if we just let 1 equal 2, we get this expression here. And then I just want to note that we still have this t dependence. To get rid of this t dependence, we need to isolate for t in our velocity equation. So with our velocity equation that we found in our other video, which is Vx equal Vox plus AXT, if we isolate for t by bringing Vox to the other side and becomes negative, and then we multiply both sides by 1 over AX, we end up getting this expression here. And now we can use this expression to plug in for t in our expression above, and this will remove the t dependence. So now from this point, we can just apply some simple algebraic concepts like distributing and multiplying. And I'm currently running out of time, so I'm just going to release a part 2 to this video, finishing the derivation.